So far we have seen about two compensation techniques. The first one being adding a dominant pole, and the second one is moving a dominant pole. In the first case, we added a larger capacitor at the output node to create a dominant pole towards the origin. But this process generally limits the bandwidth of the system by adding an extra pole to the system transfer function. Whereas in the second case, which is the moving dominant pole, where we moved an existing dominant pole towards the low frequency, thereby leading to bandwidth reduction without adding any extra pole. But this second method also requires the knowledge of the internal circuitry of the op-amp, and in both these cases, in order to move or to create a dominant pole, they both require a larger capacitor to do the job. Okay. Today we will discuss about the third compensation technique, which is nothing but the Miller's compensation technique. This is the technique which is widely used in the IC design. But before we begin the discussion about this Miller compensation technique, we will review about the effects of zeros with respect to both step response in the time domain and the frequency response in the frequency domain. So we will spend some time reviewing the effect of zeros in this first part of the Miller compensation technique video, while the second part of the video will actually discuss about the Miller compensation technique. So let's begin by considering a zero of the system that is defined as something like, out of this, the alpha factor is defined as a proportionality constant. Okay. Now the value of this proportionality constant generally ranges from 1 all the way to, say, for example, 1000. Okay. So the minimum value that it can have is 1, and it can go to a larger positive value. Whereas the factor zeta signifies the damping factor, which we have already discussed when we discussed about the frequency response, right? And the third term, which is nothing but the omega n, which signifies the natural frequency term. Note that there is a negative sign which signifies that this zero lies on the left half of the system S plane. Okay, so what I really mean here is, if I consider the S plane for the system, then this zero is actually lying on the left half of the S plane. Okay, so let me consider a second order LTI system. So normally we know that as a general second order system could be returned. So what we do here is we will try to multiply and divide this omega n square, so that the expression would right now would become. So this is a system that we have already discussed in our previous frequency response of a second order LTI system, right? So now to this system I am going to have a zero. So what I am going to do is I am just going to add this zero to my transfer function of my system. So our expression would just get modified into something like this. Now I'm just going to normalize this transfer function that I have defined, where I have a single zero in my system, and due to the second order denominator polynomial, we have two poles in our system. Okay, so I'm just going to normalize this whole transfer function by letting the value of omega n to be equal to 1. So when I do so, our transfer function would just get modified as. So this is our normalized transfer function, okay, after letting this omega n to be equal to 1. Now let me split this transfer function, the normalized transfer function, into two components. Okay, the first part of the expression I am going to denote it with a naught of s, whereas the second part of this expression I am going to denote with a term which is AD of S. Now A naught of S is nothing but our normalized second order LTI system, which contains two poles in the system. Whereas the second term, when we take a closer look, it almost reflects an identical expression that what we had in our A naught of S, except for two terms. The first term being this 1 upon alpha times that of zeta, and the second term is the factor S that is sitting at the top. So in general, the 1 upon alpha times that of zeta could be basically visualized as a gain term, if at all, if this alpha times that of zeta is lesser than 1. The value of this particular term, if it is less than 1, then the term 1 upon alpha times that of zeta would generally act as a gain term. Whereas on the other case, when this particular term is larger than the value of 1, then this particular term would act as a kind of attenuation term. Okay, so depending on the magnitude of this alpha times that of zeta, it either acts as a gain term or act as a kind of attenuation term. Now let us come back to this second term, which is the S term in the numerator. This S term has a significance in the inverse Laplace transform. Do you remember the significance of S when it is taken an inverse Laplace transform? Hope you know the answer, but still I will reveal the answer to further continue our discussion. The S in this numerator is equivalent to a differentiation in the inverse Laplace transform, right? So what we are actually doing here is that I can visualize this AD of S is actually written as something like the S times that of A naught of S, where we know that the S is nothing but a differentiation operation in the time domain. Or in other words, I can rewrite in terms of time domain, that is the AD, the response produced by the second part is nothing but the derivative of the first response. Okay, so the equivalence of these two expressions is being reflected onto this. We have already discussed about the step response of this A naught of S term, right? So now let me try to reflect the same by drawing the response. Okay, so before that I am going to assume that the value of zeta is considered to be equal to 0.5. We can assume that the poles are complex conjugate, and when the poles are complex conjugate, then the system response in general will have both oscillatory and exponentially decaying factor. So due to which I am trying to reflect the same. So assume that this is my 0, and when there is a step response at the input, then the output of a second order LTI system would grow exponentially and then settles down to the final value after some time. So as you could able to see that there is an exponential as well as a decaying factor that both combines to produce the response at the output of a second order LTI system where there is no 0 in it. So now I am going to label the step response with V naught of t. Okay, now I just want to plot function which is nothing but the derivative of my V naught of t. Okay, so which is basically reflected from our previous expression. Okay, due to the S term, we are performing a derivative on this V naught of t term. Okay, so let me have this color to represent Vd of t. So as we know that there is a kind of rate of change in my output expression due to which it goes, and since at this particular point between this particular segment of my response, you could be able to see that the rate at which the output changes is generally minimum. So due to which it all the way steps down and comes back to a value of 0, and then since there is a kind of negative slope in this case, so we end up going towards negative value, and then this is the kind of response that I would get. Okay, and now the total response, which is defined as V of t, a response that is produced by a second order LTI system containing only two poles plus the derivative term of them, which is Vd of t. Okay, so generally the response is a combination of both V naught of t and Vd of t, right? And let me draw this total response just by adding both these responses. As we know that when I try to add, the magnitude of this one would generally rise up to a large value, and after then the response would try to tend to step down. Okay, so as you could able to see that normally when I don't have any zero on my left half of the S-spline, the response that is being produced is generally slower. So what I really mean is, like, I could able to reach to the final steady state value. This is my final steady state value, which is bit slower. Okay, so it takes some amount of time to reach to my final steady state value, but the moment I add the derivative term, the response or the total response has reached to the final steady state at much earlier in my time. Okay, so I could able to reach to the final state bit earlier. So generally having a zero on the left half of the S-plane generally makes our circuit to respond faster. Okay, also one has to note that we have assumed that the value of this zeta to be equal to 0.5, and for which we know that the system poles will be complex conjugate. Okay, and I'm also considering that the minimum value of alpha to be equal to 1. Okay, due to which the factor what we had before this Vd of d term, which was basically 1 by alpha times that of zeta, in general has a magnitude that is greater than 1. So there is a kind of amplification term that appears in front of this Vd term, right? And due to which there is a kind of magnitude that goes higher. Okay, so that is the one thing that you need to note in this particular case. Okay, so let me show you a better representation of this entire graph in this next page. Okay, so as you could able to see, the one that I have drawn in the green is the normal second order LTI system where there is no zero in my system, right? And the red one which I have plotted is nothing but the derivative graph of this V naught of t along with the factor that is 1 by alpha times that of zeta that is being multiplied to this derivative of our V naught of t. Clear? So due to which we have a kind of response that goes all the way to a magnitude that is closer to the value of 1. Okay, now when we add both these quantities, we get a total response which is defined as something like V of t, and this is what would happen. And now the graph that is shown towards the right reflects what would happen when we had a value of alpha that is equal to 1, and for the value of alpha that is being increased all the way to 100. Okay, as you could able to see that the response gets degraded as we do so. Okay, so having a value of alpha is actually helps us to reach the final steady state much faster, but it also ends up having a larger overshoot. So depending on your system specification, you can choose a particular value of alpha that is required from this particular response. So now let us discuss about a zero that has been placed towards the right half of the S-plane. Okay, so a zero in the right half of the S-plane. So what happens in this case is what we wanted to discuss. So as we discussed before, I can define the same S term, and I can define an alpha which is a proportionality constant, and then the zeta factor, and then the omega n. Okay, so the only difference between this definition of zero and the previous definition is that right now the zero is placed on the right hand side, means that this term is taken as a positive quantity. Okay, in the previous case we had a zero and that has been placed towards the left half of the S-spline, and we did so just by having a negative sign over this particular term. But as of now we will consider the impact of having a zero on the right half of the S-spline by considering that the sign of this particular term is generally a positive quantity. Okay, So now we know that again when we try to write the system transfer function, I can write it as something like so. Now again one could split this entire expression into two components. One is our normal step response function, which is denoted as a naught of s, and the second one is the area of s term. Now you could able to see that there is a negative sign that appears here. So generally what does it signifies is that rather than adding the response produced by the a naught of s term and the area of s term, which is nothing but v naught of t and vd of t, okay, so in the previous case we added both the response to produce the total response of v of t, but now in this case we have to take the difference between these two expressions in order to create the response of v of t, right? So now what I can see is the total graph right now is being multiplied with the negative sign. What I really mean here is the whole of this response would go in the negative direction, so something like this, okay, and then it goes back and then settles back to 0 and then it comes something like this. So now when I add these two, the green, which is v naught of t, with this negative valued vd of t term, what happens is the total response v of t would right now become much slower. So it would look something like this, okay, so it would reach to the final state and then moves something like this. So as you could able to see that the response that due to this 0 on the right half of the s spline, the response reaches the final steady state after a very long time. So generally the circuit would respond slow when there is a 0 in the right half of the s plane. Clear? So now let's discuss about the impact of 0 in the frequency domain, and before that I will try to reflect the same as I discussed before. Having a 0 on the right half of the s prime makes the response to reach to the final steady state much slower than without having a 0, whereas when I have a 0 on the left half of the s plane, it gently aids the system to respond faster so that I can reach the final steady state at much earlier time. Now let's discuss about the impact of 0 in the frequency domain. So as we can see, when there is a 0 in either in the left half of the s plane or at the origin or even at the right half of the s plane, the magnitude of the response generally rises at a rate of plus 20 dB per decade in each of these cases. But when we come back to the phase, when I look across the 0 when it is on the left half of the s plane or even at the origin, generally the phase induced by these zeros will be plus 90 degree phase shift, okay. So any 0 that I have either on the left half of the s plane or even at the origin would induce a 90 degree phase shift, okay. But the moment the 0 shifts its location towards the right half of the s plane, then it creates a minus 90 degree phase shift, okay. So the phase degree changes to negative sign, okay. So a similar phenomenon happens even for poles, which has been produced here. So we have already discussed about it, but still I will try to discuss here. So whenever there is a 0 either in the left half of the s spline or at the origin or on the right half of the s spline, the magnitude graph, the moment it reaches a pole, the response degrades at a rate of minus 20 dB per decade in each of the cases. But when I have a pole on the left hand side or at the origin, generally these poles induces a maximum phase shift of minus 90 degree, okay. But the moment the pole appears on the right half of the s plane, what happens is the phase value of this particular pole induces plus 90 degree phase shift, okay. So which is exactly opposite in behavior with respect to the 0 that we have discussed before. So this is the response of the poles, okay. Yeah. So with this let me try to talk about a general transfer function, okay. So there are some set of terms that are being placed at the numerator, where I have zeros at the origin and some set of zeros on the left half of the s-spline and few zeros on the right half of the s-spline. Okay, so whenever I have these zeros, there is no problem, until otherwise the right half of the s-spline 0 is not closer to the origin. Okay, so this is not a problem. Origin. Okay, so generally this will not this is not a kind of critical problem, but still it might take our system to unstable, but still allow having a 0 on the right half of the s-spline, provided they are not closer to the origin. But when it comes to the poles, when we have a pole on the right half of the s-spline, then this generally creates a kind of exponentially growing sinusoidal wave. Okay, so which in general makes the system unstable, whatever type of feedback that we have. Okay, so this is not always allowed, whereas a 0 on the right half of the s-spline is allowed, provided if they are not closer to the origin. Okay, yeah. So with this we'll stop the discussion about the impact of zeros. In the second part of the video, I will discuss about the Miller compensation technique.